To graph tangent of pi over 2x minus pi over 2, we can factor out pi over 2, and then in parentheses we have x minus 1. This tells us that the phase shift is going to be 1 unit to the right, which means that the tangent, instead of going through 0, it's going to go through 1. Everything is going to be shifted 1. So the asymptote now is going to be, okay, we'll get to the asymptotes. So the period has to be pi divided by this value, by pi over 2, which is 2. Since the point of inflection is going to 1, the asymptotes are gonna go through 0, 2, negative 2, and so on. So our tangent graph is going to look like this. You can see, compared to the cotangent graph, it is not stretched like this, so you can clearly see how it changes around the x. Move on to number 11. We have 2 cosecant of 2x plus pi. 2 means the amplitude is going to be 2, so this is 2, this is negative 2. We are, same thing as in before, I'm going to factor out cosecant, I'm going to factor out 2, so then I can see that the shift is going to be pi over 2 actually, to the left, because it's a plus sign, which means that I'm going to be, okay, I'm going to calculate the period and the asymptotes now. So since this value is 2 and cosecant, like sine and cosine, has period of 2 pi, the new period is going to be 2 pi divided by 2, which is pi. Right? Cosecant is 1 over sine. Sine would be equal to 0 at pi, and 0, pi, 2 pi, and so on. But because the period is pi, everything is shrank by 2. We are going to have the asymptotes actually going through pi over 2 and so on. So pi over 2 is one asymptote. Another asymptote is going to go through 0, because 0 divided by 2 is still 0. And then we're going to have another one that goes through negative pi over 2, which means that the points, so that's how our asymptotes are going to go. Line. Negative pi over 2 is this one, pi over 2 is over here, this 0 is over here. You will have another one going through pi, right? So they should be about the same. So the points are actually going to be over here, because now sine would have been shifted pi over 2, right? So instead of starting here, it would start over here to the left. Okay, so it would go, yeah, pi over 2 starts over here, and then the sine would go like so. So that means that cosecant will have to go up here, and then the sine will go down here. So the other branch of cosecant is going to be down here, and then another branch of cosecant is going to be up here, and then those points are going to be negative pi over 4, pi over 4. I'm going to label this one is going to be 3 pi over 4, and so on. For the secant, same thing. I'm factoring out pi. So I have x plus 1/2. Period is now going to be 2 pi divided by pi, so it's just going to be 2. All right, and then secant is 1 over cosine, and cosine would have been equal 0 at pi over 2, which means that with our adjustment of period, it's going to be at 1, at 0, 1, 2, and so on. That's where our asymptotes are going to go. So that's going to be 1, 2, and so on. 0, 1, 2. And then our graph, oh, and since the period is, the amplitude is 1, so we just go from 1 to negative 1, or from negative 1 to 1. And then our little graphs are going to go, little U-shapes are going to go like so and like so. So in other words, if we were graphing our cosine would have looked like this, right? So it would be shifted 1/2. So instead of starting here, it now starts 1/2 since it's starting here, it starts 1/2 to the left. Number 13, lucky number 13, an equation for the graph a times cosine bx plus c. Let's figure out the amplitude. You can see that the amplitude equals 4. So a equals, oops, a, why not, equals 4. Then we are figuring out the period. So we can see that is the period. So the period is pi, period equals pi, which means that b has to be equal 2 pi over period over pi, which is 2. And we need to have cosine. We can clearly see that the graph is, if we would be just looking at the midline, we would say that, oh, it looks like it's a sine because it starts at the midline, which means that for cosine starts over here, which is going to be pi over 4, which means that our cosine was shifted pi over 4 to the right, right? Instead of starting at the y-axis, this maximum point is to the right. So that means that c has to be equal pi over 4, okay? But that would be if b was factored out. So pi over 4 times 2, which is going to give us pi over 2. And it was shifted to the right, so it has to be a negative over here. Okay, so that means that our equation is going to be 4 cosine 2x minus pi over 2. And we are now back to the identities. We need to verify the identities. So for this one, we have tangent squared x plus 1. I can see that that's going to be one of our Pythagorean identities. In case you don't remember the tangent and cotangent identities, you still have to remember sine squared plus cosine squared identity. And then since we have a tangent, we would be dividing by cosine squared. So if you divide each term by cosine squared, you will have over here tangent squared x, you will have plus 1 cosine squared over cosine squared, and then 1 over cosine, that is secant, and it will be squared because we divided by square, right? So we have now cosine x secant, remember it's 1 over cosine squared x, which will give us just 1 over cosine x, which is indeed secant x. Check. In this identity, I would factor out sine x, and then in parentheses, you have sine squared x plus cosine squared x, which we know is going to be equal 1. So yes, it does equal sine x. All right, over here, let's see what we can do. I don't see any specific identity, so I'll probably just convert cotangent squared into cosine squared x over sine squared x. And then I'm subtracting cosine squared x. I want to have the same denominator, so I'm going to multiply it by sine squared x, and I'm going to divide it by sine squared x. Okay, so now here I can factor out cosine squared x, and then in parentheses I will have 1 minus sine squared x, and then in the denominator I have sine squared x. Now I know that 1 minus sine squared x, look at this identity, it is cosine squared x. So total I have cosine to the power 4x over sine squared x. Or I can split it, I can actually write it down as cosine squared x over sine squared x, which is going to be cotangent, times, I can say times cosine squared x, which is this one, right? So that is equal cotangent squared x times cosine x. Check. All right, for this one, for this identity, I would probably be using my sum of sine of the sum identity. So I'm writing down sine A cosine B, sine alpha, sorry, cosine beta, plus cosine alpha sine beta, and I'm going to split this into two fractions, so both of them have the same denominator. cosine alpha, cosine beta, cosine alpha, cosine beta. So let's see, here we cancel cosine beta, here we cancel cosine alpha. Sine over cosine alpha, that gives us tangent alpha, and then sine beta over cosine beta, that gives us tangent beta. Got what we needed to get. Sine 2x is going to be 2 sine x cosine x over cosine squared minus sine squared. Oh, okay, I don't even need to do that. I'm going to erase this. I just recognize that in the denominator I actually have the double identity for cosine x. So I end up with sine 2x over cosine of 2x, which is by definition tangent of 2x. And then over here, I would probably not do anything with tangent squared x. I would try to simplify the right side. So let me see. I have 1 minus cosine of 2x. Let me remind you the identities for cosine of double angle identity for cosine. So cosine of 2x is 1 minus 2 sine squared x. So I'm going to be using this one for the numerator. And cosine of 2x also equal 2 cosine squared x minus 1. I'm going to be using that for the denominator, so I'm going to plug them in. So look what happens. 1 minus cosine of 2x is going to be 1 minus 1. This negative times this negative is going to give me 2 sine squared x. And then instead of this guy, I plug in this. So you have 1 and then minus 1, they will cancel out. And then I will have 2 cosine squared x left. So 2's cancel out, and I will end up with tangent squared x. Okay, so I simplified the right side, show that it equals to the left side. Two more identities. Secant minus 1 over tangent. Looking at the right side, the right side of this equation, I see that I have a half angle formula for tangent. So let's refresh in our memory how that is gonna play out. We have two formulas. One of them is going to be 1 minus cosine x over sine x. And that's what I'm going to try to get from this left side. So I'm going to multiply, because secant is 1 over cosine, tangent is sine over cosine. I'm going to multiply each numerator and denominator by the cosine. So secant, 1 over cosine times cosine is going to give me 1. 1 times cosine x is going to give me cosine x. Tangent is sine over cosine. Cosines cancel out. So I end up with sine x. Okay, so that is my formula. And here I have it. Okay, so again, I just multiplied both of them by cosine x, both numerator and denominator times cosine x. That's what I did there. And then finally in this one, I would have cosecant of 2 theta. I think it's 1 over sine 2 theta, right? Because cosecant is 1 over sine. And that is 1 over 2 sine theta cosine theta. Okay, so look at this and look at this. I have 2 cosine theta, and then I can say it's 1 over 1 over sine theta, 1 over sine theta divided by 2 cosine theta. It's the same thing, right? It's our simple fractions. And 1 over sine theta is cosecant theta over 2 cosine theta. So we are done with our proving identities. I'm going to pause here and then do the rest in the other video.